Alkanes represent hydrocarbons that are saturated, meaning they have the maximum number of hydrogens on them. If we start adding double bonds or triple bonds, we have to remove hydrogens or unsaturate the molecule. The molecule of butane that's drawn for you here is drawn in several different ways. This is all representing the same molecule that contains 4 carbons and 10 hydrogens. And here's one more way to draw this type of molecule, and that's with our line angle drawing, as we've done so often in our classroom. We have here 4 carbons and 10 hydrogens. Alkanes represent probably the least exciting type of molecule when it comes to their reactivity. The lower molecular weight hydrocarbons undergo combustion reactions to form carbon dioxide and water, and halogenation reactions produce many of the alkyl halides that we see used in organic synthesis. We'll talk about that type of chemistry at a later time. Small molecular weight alkanes are gases at room temperature because the intermolecular forces that hold these molecules together are very, very weak. Those are London dispersion interactions. As alkanes get larger, say pentane containing 5 carbons, the additive London dispersion interactions increase, and so these molecules are now liquids. Alkanes have a predictable molecular formula. You can see that as CnH2n plus 2, where n is the number of carbons. For our example butane, which is drawn here, we have 4 carbons, and the number of hydrogens then can be calculated by adding in that 4 for n. So 2 times 4 is 8, plus 2 is 10. Alkanes can be linear in this fashion. They can also be branched by adding additional hydrocarbon attachments. And one thing I didn't write here is they can be cyclic. For example, this 5-membered alkane. If we consider drawing a molecular structure for the molecule C4H10, there's more than one way to draw this. So we saw on the previous page that butane here contains that molecular formula, but also so does 2-methylpropane. So these two molecules here have the same molecular formula, but different atomic attachments, so the skeleton is different. Of course, they have different molecular properties as well, since they are different molecules, and we call these constitutional isomers. Depending on the substitution level of the carbon, they can have different kinds of reactivity, so it's important to be able to identify them as being different. So this terminology of primary, secondary, tertiary, and quaternary is used to identify them. Primary carbons have only one other carbon attachment. You'll notice here we use the letter R to indicate an abbreviated structure containing carbons. The second molecule is considered secondary, this one is tertiary, and this one is quaternary. So as we go down to the structure beneath, our carbon here is primary, this carbon is primary, this is primary. Here we have a secondary carbon, and here we have a tertiary carbon. Ironically, when we're discussing the substitution of a hydrogen, we're actually referring to the carbon it's attached to. And I know that sounds a little strange, but let's again look at the structure here. If we're talking about the hydrogens that are surrounding this primary carbon, their substitution level is primary, and it's because they're attached to a primary carbon. The blue hydrogens we call secondary because they're attached to a secondary carbon, and the green hydrogen is considered tertiary because we're attached to a tertiary carbon. The IUPAC method of naming organic molecules is very methodical, and it consists of a number of rules. Here's where we start learning some of those rules for simple alkanes. Linear, straight-chained, or otherwise named unbranched alkanes are shown here. There's a few of them. And the prefix we add to the suffix ane, you can see here, depends on how many carbons are in our structure. So for this molecule I'll draw here, we have 6 carbons, and so this is known as a hexane. Now you've learned how to name the simplest kind of alkane. As we look at molecules that become more complex, branching is quite common. Let me go ahead and draw an example of a branched alkane. Let's see. There we go. So according to the rules here, the first step is to find the longest chain of carbons. And if I count across, we have 1, 2, 3, 4, 5, 6, 7 carbons across. We can also try to count through a branch, for example, like this. 1,
2, 3, 4, 5, 6. That's not very long. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Seems like 7 is the longest chain. So the parent group here is heptane. Next, we need to find our substituents. So along that 7-carbon chain, there are a couple of units branching off of it. One of them's here, and one of them's here. The unit that only contains 1 carbon is called a methyl substituent. And so we already learned on the prior page that 1 carbon units use the prefix METH, and the YL that's at the end here denotes it as being a substituent. The other group there has 2 carbons long, and this is called an ethyl substituent. The next thing I need to do is number my linear parent. I know it's 7 long, but you want to number this so that your substituents have the lowest combination of numbers. If I number from the left side, 1, 2, 3, my substituents are on carbon 4 and carbon 5. If I number from the right side, my substituents are on carbons 3 and 4, and that's the way you want to number this. So we're going to call this positions 3 and 4 as far as where my substituents are. Now we're ready to name this molecule, and substituents always come first. The first substituent will have the alphabetically preferred name, so E comes before M. So to begin naming this, we start with our substituents. So we have 4-ethyl dash 3-methyl, and that's all for the substituents. So the rule is if you have no other substituents, you go straight into your parent name with no dashes, no commas, no spaces. So that's a heptane. So the name of the molecule is 4-ethyl 3-methyl heptane. Let's go ahead and look at something a bit more complex to see if we really understand. And here we'll be able to invoke a couple of other rules maybe. Okay, so there's our structure. So first thing is that we want to find the parent structure, find the longest chain of carbons. So if you go straight across, we have 1, 2, 3, 4, 5, 6. But you want to make sure you check these branches out. How about this direction? 1, 2, 3, 4, 5, 6, 7. Looks like, I think 7's our longest chain of carbons. Next, we want to number this so that our substituents have the lowest number. So I've got what looks to be a 2-carbon unit here, and I've got a couple of substituents here. And I think if I number this from the right side, they'll have the lowest number. If I were to number from the left side, or where my 7 is, if I made that a 1, then my substituents would have a higher combination of numbers. Let's go ahead and write in the substituents here so we remember them. This is ethyl. And because we have 2 groups that are the same attached to carbon 3, and they're both methyl groups, in our naming scheme we need to use dimethyl to indicate that there's 2 of them. And you want to be careful when it comes down now to naming this, because we're still going to use the M in methyl and the E in ethyl for prioritizing these as far as their names go. We're not going to use the D. That's just a numerical descriptor of how many of them there are. So this is going to come as E before M. So we start out like before. 4-ethyl. Now we'll go ahead and add our methyl groups in there. We need to say that we've got 2 methyl groups. And the way to do that here using the IUPAC name is to use the number 3 twice and follow that by dimethyl. Now the rules also now say that when we have no more substituents, we go straight into the parent name, which is heptane, but I've run out of room. So there's no dash, no comma, no space. Go straight into heptane. So the name of our molecule is 4-ethyl 3,3-dimethyl heptane.
There are some common branched alkyl substituents that deserve some additional mention here. They are highlighted in the pink color. For example, a 3-carbon linear chain, as a substituent, we know this is a propyl substituent. However, the same 3-carbon chain yet connected in the center is known as isopropyl. Let's look at an example where using this common phrasing is helpful. And I'll draw a molecule here that has 8 carbons straight across, and I'm going to attach a functional group in this position, and we now recognize that as being the isopropyl group. Well, if we use our nomenclature that we've learned prior, we count the longest chain of carbons. Indeed, there are 8 across, and we could even try numbering through this direction, but that's only 7 carbons. So this is an octane, and accordingly it would be named 3-isopropyl octane. Let's look at another example here over on the left side, where this can be actually a little tricky looking. This molecule here appears to be a butane with an isopropyl functional group, but actually, if you count the longest chain of carbons, it's 5 long with 2 methyl groups. So think about how that would be named. It's far more common to find these substituents on ring systems where the usefulness of their common name is highlighted. For example, this molecule, which is isopropyl cyclohexane. Of course, we haven't yet learned to name cyclic molecules, but that's coming up shortly.